My presentation today then is, well, the general title is Vehicle Hydrostatic Transmissions, and then that can be broken down into like 3 sections. I'm going to look at vehicle drive configurations for a particular type of vehicle. Then that will lead on to HET, which we call a high efficiency traction system, and this is for 4-wheel drive, 4-wheel motor vehicles. And then finally, I'll look at a program that we have within Rexroth for predicting the performance of vehicles with hydrostatic transmissions. This has been an in-house program for many years, but it's apt now to include this because we're going to have a version available on the internet soon for customers to use to predict the performance of their vehicles. So going to the first topic then, vehicle drive configurations. I'm going to look at a particular class of vehicle, and these are called compact vehicles in Rexroth. They're the smaller vehicles that use hydraulics, and also there are applications where it's possible to use either wheel motors or axles with high-speed motors. So these are vehicles where often there's both options can be used. So I'm going to look at the configuration of those vehicles. And I've got some experience in specifying hydraulics for these kind of vehicles. I'll just add, because of the, well, obviously I'm not going to mention any customers here or any applications that we have, either prototype or in production. For obvious reasons, there's a lot of competitors here. So I won't be mentioning that. Right. Vehicle drive configurations then, using either radial piston motors. These are our MCR motors. These are made in Scotland at Glenrothes. And these are high torque, low speed motors, so they're capable of driving wheels directly. And this one here already has a static park brake on there. That's a disc brake on the back there for parking. No pressure brake on, pressure brake off. We can also fit dynamic brakes onto these wheel motors, so you've got a complete solution. And they've got very good radial load carrying capability to support the weight of the vehicle. So these are manufactured in Scotland. So that's one solution. The other solution, of course, is to use a high-speed motor, and this is a bent axis motor, an A6VM. These are smaller displacements in comparison, relatively, and they're high speed, so you wouldn't use these to drive the wheels directly. You'd use these to drive the wheels via a gearbox or an axle as well. In both cases, the pumps used might be one of our A4VGs. This is the transmission pump, closed loop, swash plate design, and we could use this to drive both of these applications. Generally, bent axis units, whether they're motors or pumps, are more efficient than swash plate, but you can't have a through drive on a bent axis pump, so most of transmission pumps are swash plate, whereas if they're driving a high-speed motor, ideally it's bent axis, but there are swash plate motors as well. So these are the 2 drive options for the particular vehicles I'm looking at, the small compact vehicles. So if we look at the advantages and disadvantages now of these 2 options, high-speed motors, well, these are fully variable displacement motors. You can go down to 0 displacement in some cases. There's a range of control options. You can have 2-point control, switchable electrically, maximum and minimum. You can have fully controlled electroproportional displacement, or you can have displacement as a function of load pressure. I'm not going to go into the controls, that could spend a day on those alone. This is suitable for a higher vehicle speed range, and another advantage is you don't have to consider diff lock in the hydraulics. That can be catered for in the axle. Disadvantages of this system is, well, it's not a complete drive solution. We manufacture pumps and motors, we don't manufacture axles or gearboxes for these type of vehicles, so we can't offer a complete solution there. And of course, axles are not always suitable for some vehicles due to design constraints. And this is probably a higher total cost solution than wheel motors. So looking at the advantage of wheel motors now, as I said, a complete drive solution, dynamic brake, static brake, good load carrying capability. So no axles. Some vehicles are ideal without axles, give optimum ground clearance, and the space between the wheels can be utilized. Without an axle, of course, you can get much greater steer angles, which are needed on some vehicles. The disadvantages of wheel motors are they're either fixed or dual displacement. You can't have variable MCR wheel motors, so it's fixed or dual displacement. So it's one displacement or the other, switching quite quickly between the two, generally maximum and perhaps half displacement. If you use these on vehicles, you may need to include some sort of flow division to prevent wheel spin. Another limitation are the limited number of design variables when you're using wheel motors. You haven't got gearbox ratios or axle ratios to play with to optimize the design. It's pump displacement, wheel motor displacement. And as I said, these are high torque, low speed motors, so they might limit the maximum vehicle speed when you're specifying wheel motors. Okay. So if we now go on and look at some vehicles, and these options are available, as I said, in compact vehicles, and that includes ag market, municipal, and construction. So if we move on. So we're just looking at the bent axis piston motor here. In all of these examples on this page and the next page could be just one pump, one swash plate closed loop pump driving these. So if we look at the first example then, well, we'd call this heavy duty for compact vehicles. You've got a gearbox here, maybe fixed ratio or switchable ratios for maximizing speed and tractive effort. One bent axis motor, card and shaft, and two axles with diffs. So this layout is used on these vehicles. Now this isn't a common vehicle in this country. These are made in Austria and Switzerland, which might be the clue. My German colleagues call these hill tractors. They represent very high performance, gradability of 100%, that's 45 degrees, if they can get the traction, that is. As you see here, it's a general purpose vehicle. It's being used for snow blowing here, but you can put other attachments on here. This vehicle, we're probably more familiar with this in this country, a site dumper. But the site dumpers on this slide and the next slide, you'll find that this layout is common with site dumpers of a particular size, 2 to 6 ton generally. Above 6 ton, they're not normally hydrostatic. They're what they call power shift or power shuttle, which is a non-hydrostatic transmission. Below 2 ton, you'll see them on the next slide, and that's using wheel motors. These would typically have a speed of 20 to 30 kph and a gradability or gradient capability of 45 to 55%. So moving on now to this vehicle. This is a compact road sweeper. This is the largest size of compact road sweepers. The big road sweepers are truck-based, really. They use almost like a standard truck chassis with the sweeper equipment attached on top. This is a purpose-designed vehicle, but the larger size of the compact sweepers. It's road-going, so two-wheel drive is adequate for this. So axle and a bent axis motor, and here you can get the benefit of the high-speed motor. These vehicles typically can do 50 to 80 kph with this layout. And as I said, all these layouts can be fed from just one transmission pump. Final one on this page then is this vehicle here. This is again a bit of a specialized utility vehicle, general purpose. This has four-wheel drive, two axles, two bent axis motors. Beauty of this system here is there's a lot of space that can be utilised between the axles here. It's a much more space-saving solution compared to this here. So, because this vehicle will have possibly a large service pump, hopefully a Rexroth load-sensing A10 pump, to drive all the auxiliaries or attachments that you add onto it. And plus, it may have a large valve bank in there. So that space between the axles is utilised for that. Another issue with this kind of vehicle is the weight distribution can vary significantly depending on what you hang on the front, hang on the rear, or put on the back as a payload. So this solution allows you to put the traction where it's needed dependent on the weight distribution. And you possibly for road work, when it wants to move rapidly from one job to another, you might swivel one of these motors back to zero and just have two-wheel drive for high-speed travel. Okay, so that's looking at some typical drive layouts for the bent axis high-speed motor. So if we go on to the next slide, now we see wheel motor applications, and again here's the little dump truck again on both slides. But as I mentioned earlier, this is going to be a smaller dump truck, generally 1 to 2 tons. These are the smaller size of dump truck. They've got small diameter wheels, so axles on these vehicles would probably create ground clearance issues. So they use 4 wheel motors and a pump. And also, site dumpers are very, very price sensitive when it comes to selling hydraulics. So this is probably going to be the best cost-effective solution compared to the others. So, 1 to 2 tons wheel motors, 2 to 6 tons, it's what we saw on the earlier slide with bent axis, and then above 6 tons, it's generally non-hydrostatic. And I'm not just talking about one manufacturer there, that tends to be across the industry. And as I said, price is the major issue, I think, there. Well, this is a ride-on grass mower, again, 4-wheel drive. It's got different size wheels here. This is an application where you probably have radial piston motors on the front and Girota style motors on the back on some machines. And the wheels and motors are sized such that most of the traction is on the front wheels. Okay, well, moving on to the next one. Well, here's a smaller compact sweeper, precinct sweeper. This is using 2 wheel motors, and as I mentioned, these are high torque, low speed, so there's probably a limitation on the vehicle speed here, probably 50 kph is sort of the maximum for this sort of application. Finally, here's a mixed bag here. I'm not familiar with this machine, but my colleagues in Germany gave me this. So we've got mixed here. We've got an axle with bent axis and then 2 wheel motors on the back. I expect this is the steering axle, the steering pair of wheels, so you can get quite extreme steer angles here. This is grass mowing here, so this needs to get round, turn round on a sixpence to mow round bollards and telegraph poles, etc. And I wouldn't be surprised that on a vehicle like this, if this is used on, excuse me, if this is used on a golf course, it wants to get from one end of the golf course to the other, then one would put these motors into free wheel, which is quite simple with some additional valves, and then do all the driving on this axle. So that just shows not an exhaustive or a definitive list of configurations, but there's drive configurations for both types of motors. But I'm sticking with wheel motors at the moment as a lead into the next section. So, we've seen some of these vehicles already, and these are applications where you could use 4-wheel motors. And this leads into HET in a minute, which is based on wheel motor drive. So you've got the small little road sweeper here. Again, this is a general purpose utility vehicle. Grass mower we've just seen. Small dumpers. There's a wheeled loader here, small wheeled loader. There are other pictures I could put on here, but because they're specific to a particular manufacturer, I've left them out. This is a strawberry sprayer vehicle, which I'll just look at in the next slide as well. This is sort of low volume purpose designed vehicle. These sort of yellow arches include the spray nozzles, so there's two this side, two the other side, and one up the middle. So these fold out on either side, and this can spray 5 rows of strawberries simultaneously. And here's a good example where you just couldn't have axles here. You see we've got MCR motors on each corner of this vehicle, well contained in the hub of the wheel. The hoses come down these columns, and this vehicle can spray 5 rows of strawberries. Just as a side issue, when we finally look at performance of vehicles with the FADI program, when you design specialist vehicles for customers, they might not really understand what performance they require, and the guy says, well, the strawberry field's pretty flat, doesn't need much gradient capability. In my experience, I find that the steepest gradient a lot of vehicles see is driving onto the back of a low loader. If you imagine this is being taken off to some strawberry farm somewhere, it's fully fueled up and it's full of spray fluid as well. It's got to get back onto the low loader there. So it's just as a side issue, often getting onto the low loader is the steepest gradient a lot of vehicles will see. So we've looked at different motors. We haven't considered how they might be piped up yet. So I think that's my next slide. Yep. Well, this is a basic parallel circuit. Here, each motor is connected to the pump outlet port, and each return, depending on which direction it's going, is connected to the other motor, other pump port. So each motor sees the full system pressure drop across it. In this case, 400 bar. This is quite a high efficiency system, but it's got poor traction control, because you can see if all these motors are in parallel, if one loses traction, it can effectively take all the flow from the pump. And it's not unknown for somebody to overspeed one of these units and burn the motor out. So this is a parallel circuit, high efficiency, poor traction. Now, this is a basic circuit, but often this is adequate enough for some vehicles. If you're ever unfortunate enough to get stuck behind a large crop sprayer between fields, then most of them have this sort of layout, and I would say 95% of them like this, and only a few percent have some sort of traction control. So this circuit, is a practical, usable circuit in some applications. So it's high efficiency, poor traction, parallel. Here's another circuit, which is good traction control, but not so good efficiency. So you see here, these two motors are in parallel, but then they're in series with the other two motors. Hydraulic motors do not like high pressure on both ports. Well, they'll work, a lot of them will work, but in some cases you get increased leakage because you've got high pressure on this motor, front and rear, and you get increases in friction, starting torque, and increase in friction. But of course, so it's not very good efficiency, but of course it's good traction, because of course if this wheel loses traction, it can't really spin because it's in series with another wheel there. So good traction, poor efficiency, series parallel. So we've come up with what's called HET, which takes some of the benefits of both the parallel circuit and the series circuit. And that leads on to my second part of my presentation, which is the HET function. So this is very similar to that. So in essence, it looks like a series parallel circuit, but we have this block here, the HET valve block, which is teed in between these two motor lines. In this case, the flow comes out of the pump to these two motors, then flows to the other two motors, but a small flow is bled off from between these lines. So that's, if it's clearer, that valve is mounted between here. Okay? So we'll be looking inside this block in the next circuit, but at the moment you just have to assume that it's bleeding a small flow off between here. Right. So the vehicle's travelling from right to left. It's the rear motors in this case that are getting the flow first. So the flow goes through here, a little bit bleeds off, and then the rest of the flow goes on to the front motors. The motor 1 is going around at X RPM. Motor 2 is going around at X minus 2 RPM. Now you might say, well, why are these going around at different speeds? They're both on the same vehicle, same motor displacements, same tyre size. Well, at this stage, if you assume these motors are doing all the traction, all the work, then when motors provide traction, the tyre disforms and effectively the rolling radius is reduced. And I can show this in an animation at the end of the presentation if you like, but generally if you assume these motors are doing all the work, the tyre deforms, it goes around slightly faster than an unloaded wheel. And this isn't just on construction equipment or hydraulic vehicles. Normal car wheels will slip, as it's called, 1 to 3%. Now when I say slip, I don't mean skidding or spinning. This is the rotation of the wheel is fractionally lower than the vehicle would indicate because it's transmitting the torque or creating the traction. So this motor is putting out a little more flow than needed, more than the leakage, because these are radial piston motors, leakage is quite low, but we're bleeding off a little bit of flow. Excuse me. We're bleeding off a little bit of flow here. What that means is this motor doesn't get sufficient flow to create much traction. It's normally 90-10 because we're bleeding flow off. So these motors are almost freewheeling. They're being driven by the ground effectively. So what happens when this wheel starts to lose grip? It's driving over gravel or snow or ice. So we lose grip on this wheel. It's been providing the traction. Of course, now if there's no traction, there's no pressure drop virtually across this motor. So high pressure translates across and it's available to drive these motors. Now, this isn't going to spin away out of control and damage the ground or the golf course because it's still in series. It's not like it's in parallel and can take a lot of the pump flow, but there's a fractional reduction in the vehicle speed because we are bleeding this small amount of flow off here. So we've got torque on the front axis. It's going around fractionally slower, but imperceptibly. And of course this works without any driver input. You get traction transferring from the rear axle to the front without any real driver input and without any perceivable change in speed. Like I said, this motor's going now around slightly faster than this because this is providing the torque, but not in an uncontrolled manner where it can damage the ground. Okay, so if we move on now and look internally at this block. So here's the transmission pump here with the normal components you would have on a transmission pump. And here is the HET block here. Now, there's a lot of features in this block which you might recognize, which are standard to transmissions. So there's the flushing valve here. We've got relief valves and we've got anti-cavitation check valves. But the essence here of the HET are these two small pressure compensated flow control valves which bleed off this very small amount of flow from between the lines. And that is the basis of HET. If we look at some of the advantages then here, this is in production on some vehicles. It's got a proven higher efficiency than some other systems and it's more cost effective than some other systems. And it's got good traction under wheel spin conditions. It's quite simple compared to some systems with regard to motor piping, etc. These are standard motors. They've not got additional ports or anything. And you minimize piping, leakage points, and assembly and maintenance, because it is quite a simple layout. And hopefully it's going to become simpler because we're developing that manifold that you saw in the last slide. We're developing this as a part of the wheel motor casing to simplify it even further. One of the big advantages of this system is that in some of our competitive systems, they have to use fixed displacement motors. We can use dual displacement motors on the HET, so you can have high displacement, low speed, high torque, and then switch the motors for higher speed, lower torque applications. And as it says here, the HET manifold includes anti-cavitation flushing as standard, but we're looking to put the HET into the motor housings themselves. And then to summarize then, so here's a dump truck with the HET. So if the rear wheels begin to spin, then torque transfers to the front wheels. The rear wheels have nearly the same speed as the driving wheels, so they don't spin excessively and cause damage to the ground, and full driving torque transfers to the other axle. This is the result, really: increased tractive force on difficult terrain, improvement of gradability, increased tractive force for overcoming obstacles. And if you go on YouTube and type in HET Rexroth, you can see one of these vehicles, and you can see a good animated description. And you can also see competitors' machines as well. There's a good clip where it's obviously a test ground somewhere. The vehicle's on a slope, and inlaid into the ground are these rollers. So the vehicle's going up the slope without any traction control. As soon as one wheel hits the rollers, it spins, and the vehicle doesn't progress any further. Well, that would be the same result with the HET function. As one wheel slips, traction is transferred to the other axle. So that's the second part of my presentation. If we move on now to the final part, which is the FARDI program. As I said, FARDI is an in-house program for simulating or predicting the performance of hydrostatic vehicles. You can see where FARDI comes from now. It's German, it's a FAR diagram, so it's the letters F-A-D-I there, which equals drive diagram. And I have FARDI on my laptop, and really the best way to use the FARDI program is to go to a customer with it and attach your laptop to an overhead projector, and then go through with the customer all these input data: vehicle weight, laden, unladen, engine power, the speed, etc., and then look at what tractive effort and what work mode or track mode he requires. You can alter wheel diameter, rolling resistance. You can even include wind resistance if necessary, if your vehicle goes fast enough. You can change axle ratios, gearbox ratios, and of course operating pressure. We've got high pressure and medium duty pumps. If you can save money by using a lower operating pressure, then we can use the A10 VG rather than the A4 VG. But these are some of the parameters one would look at. And as I said, hopefully soon this will be available for customers to use on the internet. So if we look at some output from FARDI diagram, and this is a very, very simple graph. I've just used something very simple so you can see the fundamentals or the essence of what it does. So here is the tractive effort. This is basically the pulling force of the vehicle plotted against the velocity here. And this is quite a simple system. It's a single pump with two fixed displacement motors. So the pump is changing displacement from here to here, and then that's the maximum speed, because you can't change the motor displacements any further. So you've put in a rolling resistance dependent on the tyres and the ground it's running on, and at minimum vehicle mass you've got this line here. So this shows the vehicle can reach a speed of 19 kph. Even with it fully loaded with the rolling resistance we've selected, it still go up to 18, 19 kph. This is a line of constant power determined by the engine power you've put in. You increase the engine power, you move in this direction. Reduce the engine power, this curve moves this way. So the vehicle is basically capable to operate under this area here. And as you can see, it can go up a gradient of 5% right up to full speed. But I've inputted another gradient here of 25%, and you can see here, which is quite interesting, the vehicle can go up a gradient of 25% if it basically gets a run at it between 2 and 6 kilometers per hour. But it wouldn't start on a 25% gradient, because this line here, if we weren't taking into account the starting torques and inefficiencies of the pumper motor, this line would come across here. But as you see, it slopes up. So it's a good case where you take a run at it, the vehicle can get up a 25% gradient. If it stops, it might not start again on that gradient. And you'll see on the next graph, I put another gradient of 15%, which means the vehicle can obtain 10 kilometers an hour on a 15% gradient. But this is a very simple graph. If I put more on it, I would confuse you, I expect, if I haven't already. You can include efficiencies. You can plot one on top of the other to see the small effect of changing various parameters. And what I did in the next graph, I left everything the same. I just made the motors dual displacement. So they go from, you can switch them from max to half displacement. So 1 to 2 is really the same as the previous graph, but now we've got 3 to 4 where the motors are on half displacement. So you can see now we've got a good overlap here. So in this region, the vehicle can be in either gear, which is good. They're not far apart. When I say either gear, either displacement. But we can no longer, at half displacement, go up a 5% gradient. We can get just a fraction more, perhaps. And here's the 15% gradient. So we can't do anything fully loaded on a 50% gradient at half displacement. But we can get 10 kilometers an hour out of the vehicle. And of course, this hasn't changed here, the 25% gradient. So this is the sort of graph or output you can go through with customers. And you know, we've only got single lines on here, but behind all these lines are all the embedded efficiencies of the pumps and motors within Fardy, the starting torques, the gearbox inefficiencies, etc. So there's a lot behind these single lines on a graph. Now, if anybody wants a more detailed Fardy diagram, I've got some here that I can hand out. I've only got 40 for the whole day, but you know, it shows a lot more information on there for a particular vehicle. That's looking at one vehicle and just changing the power. This is some of the data, the input and output data for the first diagram you saw. So this is vehicle minimum mass 4,100 kilos, fully loaded 6,600. Got a rolling resistance here of 0.025, and we've got a table of those for different tyres, different ground conditions, etc. Static wheel radius 0.315, and you've got engine speed here, charge pump power loss. There's no gearboxes. There's the pump displacement, and this is the actual conditions at each of those points. So I've looked at Fardy in reverse here. I've looked at the output. Now I'm going to look at just a few slides on the input. So hopefully you'll be able to use this one day on the internet soon. So this is a typical page or typical layout from Fardy. So navigation is here, and by navigation I mean this is where you select what you're putting the data in for, the engine, gearbox, a pump or a motor. You select those and then you enter the data here, and immediately the effect is shown on the graph or output here. So this is the standard page for data entry. Now if we look at a data entry for, say, a pump, so you can choose the delta P here for the transmission, 420 bar. You can add fixed losses if you like, if it's a long distance between the pump and the motor, or you've got some additional valves, you can take their pressure loss into account. Here is the families, different families of pumps, Rexroth pumps that you can choose. So we've got the A4VG here, so you might choose that one as we have here, and then choose the displacement, 56, but perhaps you want to stop the pump down, you don't want to use the full displacement, so you can put the maximum displacement in here. You can choose a different charge pump size and also charge pump pressure. So this is just a typical input for one pump. You might have another pump also supplying. You can add information there as well. And now, last but one slide. This is a typical page for the motor. It's an A6VM, a bent axis here. Often the customer wants to know, oh, what's the maximum speed I can get out of my vehicle? So you dial in the speed here, and then this works out what's the minimum motor displacement to achieve that speed. And at the same time it shows you, well, are you getting into the red on the motor speed? You've gone down too small a displacement, you're right up on the limit of its speed. Well, in this case it's okay. Also, it gives you an indication of the efficiency as well, 60%, so we're not in the red there. And also it shows you the tractive effort. So you can use this to play around with the customer and find out the maximum or set the vehicle speed, and then find out what the minimum motor displacement was. And you might say, oh, well, that's too small a displacement, let's change the motor size. And I think my next slide is the final one. Yes, I'd just like to acknowledge my colleagues' help in feedback and some of the pictures on this presentation. There's Ian, he's at Glenrothes at Scotland, where the MCRs come from. And these are my colleagues from Germany who are not only experts in pumps and motors, they're also experts in particular applications.